So let's do a computational problem and apply the second partial derivative test. We have a function and we like to find the local extrema of this function. So two things. One, we first need to find critical points, right? And two, then we need to evaluate the determinant of the Hessian, so that's what I call D here, and fxx. Okay, so you will have fxx when you compute these. So this is not something extra. I'm just pointing out with the value of D and value of the second derivative fxx at critical points, then you will be able to use the second partial derivative test to figure out what kind of local extrema you have. All right, so let's go ahead. By the way, to find critical points, you need to find df dx and df dy. To find the Hessian, you need to find df dxx, fxy, and fyx, and fyy. So you need 3 second derivatives. All right. So let's go ahead. One. I'm going to just compute df dx. Looking at this, I have a polynomial treating y as a constant. Df dx is minus 3x squared plus 4y, and this part is constant, so it goes away. Df dy is equal to, okay, this goes away because it's a constant to y. This becomes 4x and minus 4y, okay? And they are defined everywhere. I just need to find the points so that both equal 0. So I said this partial derivatives equal 0, and go ahead, solve for x and y. Okay, so fy equals 0 tells me x is equal to y. All right, and now I substitute x equal to y into the first equation. I get, so I'm gonna replace y by x and see what happens. So minus 3x squared plus 4x equals 0. Now I get x times minus 3x plus 4 equals 0. So this tells me either x equal to 0 or this part of the equation equals 0. So I'm gonna have x equals 0 and x equals 4/3. And remember, x is equal to y. So when x is equal to 0, y must equal 0 as well. And when x equals 4/3, y equals 4/3 as well. So they come in pairs. All right. Okay, so this would be the critical points that we have. Now let's go ahead and find second derivatives, second partial derivatives. Okay, so from df dx, I have fxx is equal to minus 6x. I look at this, treat y as a constant, find the derivative. Now fxy, okay, treat x as a constant, focus on differentiating y. So this goes away, this is equal to 4. Now, I also need to find the fyy. This is constant after the derivative goes away, and this gives me -4. All right, so the d is equal to the determinant of -4x, 4, and -4 there. Okay, determinant of the Hessian. So here I get 24x minus 16. Okay, so this is my determinant. And now I just need to say 3, apply the second partial derivative test. Okay, so d at 0, 0 is equal to -16. I plug 0 into the x, there's nothing for me to plug 0 into the y, so just 0 minus 16. D negative, what does the test say? When d is negative, I have a saddle point at 0, 0, and f of 0, 0. So saddle point 0, 0, f of 0, 0, so 0, 0, 0, and plus 1. So this is the point on the surface, it's a saddle point. And the other critical point, okay, so here I have 24 times 4/3 minus 16. So simplify this. 32 minus 16. That's 16. This is a positive. And now I need to further look at what happens for the fx at the critical point. So this is, let's look at the second derivative here. So this is minus 24/3. This is a negative. So negative means what? Negative means it's opening downward. If it's opening downward, it looks like this, right? So the point will give us a local maximum. Okay, so I'm running out of space. I'm gonna just squeeze in here. So I have local max at 4/3. F of 4/3 would be the local maximum value. All right.